Hi, everyone. All right, well, now we're ready to begin our next big topic in our course, which is nanostructures. You'll see that nanostructures is going to draw quite a bit on what we've learned already about materials and semiconductors, but it's a distinct topic too. And it's become important as people have learned the ability to make tiny, tiny structures which behave according to the rules of quantum mechanics. So this video will just introduce the idea, and then the succeeding ones will start to dive into this subject in more detail. Here, hang on one second. So at the outset, it makes sense to ask, well, what is a nanostructure? A nanostructure is a sample of material or a device that has at least one dimension on the nanometer scale. Meaning 10 to the minus 9 meters. Pretty straightforward, right? And these materials with these small dimensions, the devices with small dimensions, are small enough that that structure can create a confining potential for electrons or holes. Okay? Okay? And so another way to think of nanostructures is that there are structures that are small enough that the effect of this confinement produces measurable effects. Okay? In other words, a nanostructure is a system that shows quantum effects due to electron or hole confinement. Okay? So that's what we want to investigate. So here, let's just try to get an idea of what that might mean. So for example, we're going to find that electrons in a confining potential can be treated like can be treated like particles that have an effective mass. And so when we look at the effect of the confining potential, we can write down Schrodinger's equation much as it normally is, but where the mass is replaced by the effective mass. This is called the effective mass approximation. And in the effective mass approximation, an electron or a hole can be treated as a particle, but a particle with an effective mass m star. And now, with that idea in mind, let's consider the following simple example. Suppose we have an electron that's trapped in a structure that has thickness or width or size of 10 nanometers. And that's kind of an interesting length because that represents about the state of art of photolithography with extreme ultraviolet radiation. In other words, it's the state of the art today, okay? Similar sizes can also be reached in a laboratory less expensively with a technology called electron lithography, electron beam lithography. But in any event, so suppose we have a structure that has a characteristic thickness or size or dimension of 10 nanometers. To a first approximation, we might think of this confining structure, oh my God, as being like an infinite well. The electron is confined in the structure okay? Then we would expect to get under the, then we would expect to see effects due to quantization. In other words, we'd expect to see quantized energy states. All right, of course, there are many types of confining potentials. It doesn't have to be an infinite well, but the infinite well is the simplest one. So it's definitely a place to start. Then we know that the quantum states, the energies would be given by the following. It's just h bar squared pi squared over 2m star L squared times n squared, where n is a quantum number. And now, let's imagine for an electron in silicon, what the energy would be for a 10 nanometer wide structure. In particular, let's figure out the energy required for a transition from the n equals 1 state to the n equals 2 state. Okay, and of course, this is a simple problem we've solved before. This is just equal to 4 minus 1 or 3 times 1/2 h bar squared pi squared over m star L squared. Okay, but now let's put in numbers appropriate for this problem. So then L will be the thickness of our layer. We said 10 nanometers. And m star will be the effective mass of the electron in silicon, which we'll just take to be 0.1 times the actual mass of an electron, which is about right. Actually, in silicon, the effective mass is different in different directions. So there's something called the longitudinal mass and something called the transverse mass, and they're not the same. But the lighter one is about 0.1 times the mass of an electron. So we can take this to be about 1 times 10 to the minus 31 kilogram. Okay. So go ahead now and figure out the transition energy from state 2 to state 1. Okay. So maybe even pause for a second until you figured out the answer. All right, once you found the answer, you should find that the transition energy is on the order of 0.05 electron volts. So it's a small energy. But note that even at room temperature, Boltzmann's constant times T is approximately 0.026 electron volts. So that means that E21 is greater than KT at room temperature. In other words, we would expect a device of this size, 10 nanometers thickness, to exhibit quantum effects. And those quantum effects might even be visible at room temperature. And that's kind of interesting because that means that an object of this dimension is a nanostructure. And gosh, that means that the smallest transistors and other feature structures that are made with photolithography now actually are nanostructures. Now, of course, even larger devices would show some quantum effects at smaller energy scales. And if we were at lower temperatures, they might still count as nanostructures too. Anyway, so that's what a nanostructure is. And what we're going to explore in the next few lectures is what kind of nanostructures people are making and how they make them and what some of their properties are, and even what kind of devices can be made from them. All right? All right, well, I'm gonna stop this video now. We'll take this up in the next one.